Okay, so this is sort of an ad hoc explanation. This is mostly unplanned, and if I stumble, I'm not going to edit it out. So, yeah, this is just an off the cuff kind of thing. So, a little bit of background. If you have an equation of this format, so x, let's say, over a squared plus y rather, over b, there's an example, not going to edit that out, equals 1. You get an ellipse, right? It's like a squash circle, and A and B are the minor axes. So if the auto line tool will work with me. So if I make an oval, and that's pretty good. It's off by a bit, but whatever, close enough, right? You get a shape like that. If you have something of the form a, or rather x over a squared minus y over b squared equals 1, then you get something like the following. We're going to run out of room pretty quick. So y-axis, x-axis. For this one, you're going to have asymptotes along some diagonal lines, some lines, and the slopes of the lines are basically the ratios of A and B. I forget which is which, but those are details we don't need to work out right now. And you get a graph like this. Okay. So if you have something of this format, and let's put B first. B will always go with Y. And it's definitely off the cuff, because really I should have done a circle first, but that's okay. Then you will get something like this. And maybe I'll shrink these down and kind of block them together into one smaller section. Actually, I think that's a good idea. I'll probably do that. So asymptotes. And we get something like this. Okay. And then circle. If you do something like this, x squared plus y squared equals r squared, right? So these are all conic sections, right? Circle, auto circle tool, don't fail me now, something like that. Notice that none of these are functions, right? And what I ought to do probably is take, oops, wrong tool. Take this guy. In fact, let's do this. Okay, it doesn't want to do that. Okay, take all this, shrink it all down to like that big. Put the circle up here with the ellipse. And then put the two hyperbola together. That one can go there, and that one can go close enough. Cool. Okay. So these are some different options for equations that have graphs but are not functions. And in particular, this one is really hard to make into a function. These not quite so. It depends on what what you want it for. So basically, for all three of these, they all fail the vertical line test, right? Because they hit plenty of vertical lines more than once. So, for example, if we wanted to take some sort of equation that ultimately makes a circle and get it to be like a function, right? Then we'd have to do something like this. If we had like x squared plus y squared equals, say, 4, I can subtract x squared on both sides. And then, as we say, square root it, right? But you end up with this problem. Plus minus the square root of 4 minus x squared. I want the section to be either the top section or the bottom section, but which one do I pick, right? There's no single correct way to go. So if this is an implicit solution to a differential equation, which I'll just call DE, differential equation. Then which one you pick, top or bottom, depends on what you're going to use it for. If I said, oh, well, I want the pair that goes through the ordered pair at 2. Is it 2 root 2? Is that what I want? Or just root 2? Yeah, root 2, root 2, right? Well, that ordered pair, root 2, is here. It's in quadrant 1, so I want the top half. So if I do that, then I need to say, okay, I need the top half. So I need to go with the positive version. So I'll say y equals the square root of 4 minus x squared, discarding the minus sign because it's not the bottom half that I want, it's the top half. And that is determined entirely by, well, which ordered pair is your graph need to go through. So these are all conic sections. They all kind of work in a similar way. This one's a little bit messier because you get 2 disconnected pieces, but you can do this with any of these. What if you have something like the following? What if you have your solution that looks like this? Let's say x squared minus y squared equals 0. What does that graph look like? What are the ordered pairs that make the solution? So let's think about this. And we could make a t-table, go back to plotting by a t-table. If you don't know what it looks like, just get started, right? So let's say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and then 1, 2, 3, 4. Okay, close enough. It's gonna bother me if I don't fix that. Also, I'm not gonna edit this out. 1, 2, 3, 4. Okay. So we could say, well, let's make a t-table. That's not the only way. It's not the best way. But let's just start that way. Here's x, here's y. Well, if x is 0, we'd have 0 minus y squared equals 0. So it will be the solutions. Well, just 0. Okay, cool. So the origin, that's a solution to the equation. Okay. What if we went with like 1? Okay, so x squared, x is 1, so x squared would be 1 minus y squared equals 0. Add y squared to both sides. Now I have 2 solutions. I have 1 and negative 1. I have plus minus 1. Right? It's not a function, it's just an equation. So when x is 1, y could be 1 or negative 1. Okay? Well, what about if x is, say, 2? Okay, so 4 minus y squared equals 0. So 4 equals y squared. So y equals plus minus 2. So over here on my graph, and it's kind of like an absolute value function sort of thing going on. Okay, let's do some negative values. I think I know what's going to happen with 3, right? Y will just be plus minus 3, and in fact, I'll just sort of assume that that's right. You can check for yourself. So like here and here. Okay, so what if I plug in negative 1? Okay, so negative 1 squared is still 1. And the equation is the same as that equation. So I get plus minus 1. So here, uh, and, okay. And you might see where this is going. So what about negative 2? Well, negative 2 squared is 4 minus y squared equals 0. Hey, that's the equation that got us 2 and negative 2. Okay, and I bet you we can cut corners again, and I'll let you check for yourself. And of course, I'm hand drawing this. It's not perfect, but you get the idea. Okay, so get this big X. And I talked about the conic sections having A's and B's, different coefficients or whatever, different parameters to make the shape different. This is also a conic section. It's just not one you usually see. So this is like if you have, well, that was actually pretty good, so I guess I'll keep it. If you have your cones like this, that was not as good, but whatever. And if you just slice, I can't like I'm motioning with my hands, slice down the middle. But if you cut, I don't know. It's hard to say without. If you have like I don't know, big Santuco, right? I'm this is a terrible knife, but if you cut down and you cut across here and then across, sorry, struggling with the interface, cut across here, you cut down, you're going to cut through these edges and through this edge. And of course, the cones don't really stop. They go on forever, right? In the conic section. So these aren't really there. But you get instead this cut of the conic section. So this is another conic section that maybe you've never seen before. What's the efficient way to draw this? Well, let's look at that. Because this was really tedious. I don't want to do this every time. And then I got to, show off my amazing drawing skills. So what's the best way? If I factor the left-hand side, I can do this like I'm solving a quadratic equation. Say, oh, well, if I factor it, I can separate the factors and say, well, either x minus y equals 0 or x plus y equals 0. Okay? So either y equals x or y equals negative x. So if I go to draw this, okay, well, I got y equals x. I'm hoping the auto line tool will help me out here to make because it'll snap to 45 degrees. There we go. And I just have to then put it into place. There we go. Okay, close enough. Not perfect, good enough. Let's snap, maybe. There we go. Now, of course, this is not a function. This fails the vertical line test. So if I want a function for my solution to something, right, a differential equation, if I know that I want this point to be part of my solution, then really it's this entire line that is the solution to the differential equation. If I want a function as a result, now I'd say that my solution is y equals x, not this equation. It's this equation, which I could, if I wanted to, leave as this equation. It's an implicit equation. So how would this look with a different one? So what if I had something like this? What if I had, and I'll choose convenient numbers so we don't have to deal with the roots. 4x squared minus 9 y squared equals 0. Well, this factors as 2x minus 3y times 2x plus 3y. Plus looks a bit like a t, but it's a plus. So that means either 2x minus 3y equals 0 or 2x plus 3y equals 0. If I want, I can solve for y in both of these cases. So negative 3y equals negative 2x. So y equals 2/3 x. I said we would avoid roots, not fractions. So we're going to be stuck with fractions. And then here, 3y is negative 2x, or y equals negative 2/3 x. Notice how the two slopes are equal in absolute value, which is sort of another hint, which maybe we'll get to. We'll see how long this video gets. So if I want the solution that goes through the ordered pair 3, negative 2, okay, write that better. Then if I draw these out, which is not necessary, but it's one way to do it. So my slope is 2/3. So I want something roughly like this. Let's say that's a slope of 2/3. And then this one off a bit. Let's say that's good enough. Well, 3 negative 2/3, that's going to be over here. So I want this as my solution to the differential equation, because this other one does not go through 3 negative 2/3. I want the one with negative slope. I want this one, which I could say, well, I want to express it implicitly. If that's the case, then this is the equation, or probably even better, this is the equation. Okay? So, what's another aspect of this which might help? If I had something like let's go back to the previous example. Get another view on it. I could add y squared on both sides, and then I could, in air quotes, square root both sides, right? So on the left, I get the absolute value of x, and on the right, I get the absolute value of y. So that's why whenever I'd say, oh, what if x is 3, y is plus or minus 3? What if x is negative 2? Well, then y is plus or minus negative, or plus or minus 2, rather. You probably could take this approach with absolute values to this example and others like it. I'm not sure it's really beneficial. I think the factorization approach is probably makes more sense. Anyway, that's just sort of some background on how to deal with some conic sections um, in order to help solve some differential equations where these come up.